For our next keynote, there'll be two gentlemen coming up and a special guest that they'll be introducing. Vladimir Alves is co-founder, CTO at NGD Systems, where he focuses on developing system-on-a-chip that implement intelligent storage technology for data centers and fog computing. He has developed SoC-based solid-state solutions for over 10 years, during which his teams have released many enterprise SSD controllers. Before he co-founded NGD, he was Senior Director of SSD System-on-Chip Development at Western Digital and STech. He's the author of over 30 scientific publications on subjects including SoCs, computer architecture, and co-author of over 20 patents. He earned his PhD in microelectronics from the National Polytechnic Institute of Grenoble, France. Along with Vladimir, our first keynote presenter is Scott Shadley, who's VP of Marketing at NGD, where he leads marketing, product management, and product development for the company. The whole area of computational storage that is starting to take off, he's the key figure in promoting that technology as the co-chair of the SNIA Technical Working Group on that subject, and he helped found that particular group. And he's speaking on the subject not only here at Flash Memory Summit, but also at the Open Compute Summit, NVMe Developer Days, and many other events, press interviews, blogs, and webinars. Before joining NGD, Scott managed the product marketing team at Micron for the business line management of SATA SSD portfolio, and was the principal technologist for the SSD and emerging memory portfolio for that company. He launched 4 successful innovative SSDs for Micron and 2 for STech, all of which were multi-million-dollar successes. Scott has an MBA in marketing from University of Phoenix, earned his bachelor's electrical engineering and design physics from Boise State University. Now, those of you in the audience who might be college sports fans might know the Boise State Broncos and their official mascot that I'm sure Scott will be talking about, who was Buster Bronco. So with no further ado, ladies and gentlemen, please welcome Scott Shadley.
Thank you, Jay. I didn't know I got to talk about Buster. I spent last keynote last year, for those of you who joined us on Thursday, doing a little bit of a football analogy, so it was kind of fun there. Great to be here today. We're going to take a little different spin on kind of the presentation efforts. We wanted to talk to you a little bit about what the technology is doing and what you can do with this technology, not necessarily just from what an NGD product is, but what the market's available to do. And so with that, one of the biggest things that we have that we're all dealing with today, and you even heard from Jillian, is data, and a little bit more data. So the question is, what are we going to do about all of this data? And the easiest thing for me to do is to actually step back and let you watch a quick video of everyone else telling you what you need to do with your data.
Cloud computing alone is not going to be adequate anymore to support the emerging Internet of Things.
Internet of Things is approaching us faster and faster. Things like your fridge, your dishwasher, your coffee maker will all have their own internet connections, and they will be able to gather data.
50 billion networked devices?
50 billion devices connecting, driving traffic. It's not the devices so much, it's the amount of data that is just growing exponentially.
At a certain point, the pipe cannot support any more data.
One of the problems that has plagued cloud applications is the latency required to get data back and forth to the cloud.
It just functionally wouldn't work. There would not be enough bandwidth. The servers themselves would get overloaded,
burdening the network with more and more traffic.
You really need to have a device that can process the information that's coming in real time.
As these new use cases evolve, the autonomous car, the connected plane, you've got this need for speed and latency and locality of compute that's going to drive you to do some of these functions at the edge.
When it comes to making important real-time decisions, edge computing significantly reduces the latency.
Instead of us adapting to computers and having to learn their language, computers are becoming more and more intelligent in the sense that they adapt to us.
It is estimated that 45% of created data will be handled at the edge. That means storage, processing, analytics, and decisioning.
And that's going to drive a need for some new capabilities and new technologies.
So as you just heard, data is a problem, and where is the data being generated? What is causing that data generation? It all has to do with where the data lives. The data lives on storage, and today we're talking about flash, of course, Flash Memory Summit, and the fact that we've got a lot of innovative talks. You just heard from our friends at SK Hynix about some of the innovations they're doing at the media level, at the PCIe interface, NVMe. All of this is very beneficial to the market, but we need to take it to another level. As Jay mentioned, there's been a lot of work in this concept of computational storage. We're very proud to be a member of NGD Systems, where we've taken this traditional solid-state storage device and we've added a little extra oomph to it. And there's been presentations in the past, even on this same stage, about products that are allowing you to put compute into a storage product. What we're doing uniquely is we're actually giving the customer the ability to plug and play an NVMe device and have the application migrated into the drive and do some work from there. Now, I don't have a lot of time today to get into the nuts and bolts of our specific solution because we'd rather give you some little bit of technology awareness through my CTO and partner, because he tends to be a much better speaker than myself. So feel free to stop by and see us later today, because it's not about the data, it's not about the storage, it's about how we get results from that data and where those results are generated at the location that they're made. If you look at the very simple example as a marketing guy I can come up with, you've got a bunch of noisy data and you've got to filter that data, and the only way that you can filter that data effectively today is to move it. And as you move it, you lose data, it takes time, and those are all measurable facts and bits of information that we can overcome with the technology. And as you can see here, our friends at Gartner even said by 2022, more than 50% of the enterprise-generated data will be created and processed outside the data center or in the cloud. And so as part of this, we thought it would be very beneficial to bring up a partner of ours in the way of Jonathan Hinkle, an executive director and distinguished researcher at Lenovo in the System Architecture Group, and he also happens to be a founder of the EDSFF form factor. So Jonathan?
Hello there. So I'm going to talk about the sharp edge. So as you probably just heard, why should we do more at the edge? We have a lot of sensors and just an incredible number of devices, billions of devices out at the edge, all creating data. And with all the different verticals that are growing for the edge, then that's just going to be a huge data deluge of just amount of data is just amazing. But it's expensive in cost and power and performance to move all that data to the cloud every time. And there's a lot of different special requirements you have specific to the locality of the devices, to the security, along with the latency and the power. So we want to do more at the edge, but their needs are very different from the data center. The space, it's a lot more space constrained, so we need small form factors, density and modularity, and also the power. It needs to be low power, not just for energy, in case it has a battery or some kind of energy source, but low power for thermal reasons as well, to be cooled. So several years ago, a group that we founded, EDSFF, we focused on data center, the enterprise and data center, and forming a new type of drive, NVMe drive, that would focus on the needs, what we need there, what you can do on flash. And so we have these now, they're standardized, they've been standardized March of last year and doing really well now. And they have some interesting attributes though that actually make them very well suited for the edge. So they're much smaller, and E1.S drive here, you can see it's much smaller than your D.2, gives you better airflow, and you can scale resources very easily in a modular fashion. Also, another way to solve the problem of what we have at the edge, computational storage also aligns to those needs. It also can lower power by reducing the amount of data that has to be moved back and forth from the processor to the storage and back and forth. And also the processor, if we can do some processing in where the storage is, where the data resides, then we don't have to have necessarily the highest power processor, which is harder to cool. Also, we can have the parallelism. We can leverage the parallelism of all those devices together to get faster results. And you can scale resources in increments that you can balance basically the performance of compute versus the capacity. So again, like with computational storage, back and forth, that data movement is reduced. But also, I appreciate what my friends at NGD Systems are doing, because not only can we do EDSFF E1.S, but we can also do that. And so here's the first E1.S NVMe drive. that has computational storage as well. So very exciting. All right, and now I'd like to call up Vladimir, the CTO of NGD, tell you a little more about computational storage. Thank you.
Okay. Thank you very much, Jonathan, for the introduction. Okay, so today I will talk a little bit about NGD Systems' effort to bring machine learning where data resides by using computational storage. So it's now common knowledge that AI is an indispensable dimension in our society, an engine for radical modernization in medicine, entertainment, transportation, and much more. So deep neural networks, CNNs, RNNs, are today's dominant high-end models providing highly accurate and complex engines or powering those engines. However, DNNs have a terrible carbon footprint. For example, training an AI deep neural network can produce as much carbon as 5 cars over their entire lifetime, which was a surprise when I read this article. It's shown in the slide, which doesn't seem to be sustainable in the long run. Machine learning is a subset of AI defined as the scientific study of algorithms that computing systems use in order to perform a specific task without using explicit instructions. And machine learning needs data, a lot of data. Data when it needs to be trained, data to extract information and knowledge for inference, for example. Where is that data kept? Especially big data. In storage devices, obviously, and it is increasingly being generated, stored, and processed at the edge as opposed to the centralized cloud. So which begs the question, does in-storage machine learning make sense? Could machine learning applications run in storage? So we're going to try and answer some of these questions for you and give some examples. So the very first step towards the perceptron that we use today in neural networks was taken in 1943 by McCulloch and Pitts by mimicking the functionality of a biological neuron. The next major development after the MCP in neural networks was the concept of a perceptron, which was introduced in 1958. So neural models used today in RNNs, CNNs, and DNNs implementations everywhere originate from that early perceptron model. And in most cases involve complex mathematical operations where synaptic weights store the information. But there are other types, many other types of models, neuron models, some with very interesting properties, like the weightless artificial neural networks that I'm going to talk about a little bit today. So the theoretical work behind such interesting neural networks dates back to the early days of the research in the field. These networks are based on the biological neurons dendritic tree, and it's a pattern recognition system whose main difference from other learning methodologies lies on the direct use of information stored in random access memories. Weightless neural networks operation uses the input to build a set of addresses to access RAM node's contents. Each node is assigned to one of the classes of patterns to be recognized. This means that the number of nodes in such a network is the same as the number of classes that you are trying to recognize. One very important aspect of weightless neural networks is that training mostly involves decoding addresses and reading and writing from a memory. This makes for a very interesting compute versus trade-off, compute versus memory trade-off that we're going to try and explore. So what benefits can we expect from using weightless neural networks applied to machine learning specifically? So first of all, speed. Because both training and inference are extremely simple, requires less client time, less processing time, and less energy is used. The model has multiple independent components, which can be easily parallelized, and we're going to take advantage of that. Parallel training is similar to a parallel sum, which means that no training is lost when using a federated approach, and accuracy is kept. And last but not least, a very small hardware footprint. thanks to that advantageous memory versus computing trade-off that I talked about previously. So let's give some examples of weightless neural networks applied to real cases out there. So this example shows like a little complex network. It's called a wizard ensemble with multiple discriminators per class. This multi-tracker runs smoothly even on an ARM quad-core processor. Here we can see online training happening with different aspects and poses of the same object associated to different discriminators. Another interesting example, Wizard has also been used as a very efficient way of performing facial emotion classification. The accuracy results are comparable to those obtained with state-of-the-art convolutional neural networks. In contrast, the average Wizard training time per image is significantly smaller than what can be achieved with convolutional neural networks, which shows its potential applicability for edge computing, for example. So weightless neural networks have also been successfully used in many other areas or examples, such as financial credit analysis and speech recognitions, among others. So what's next for us at NGD Systems? So beyond the adoption of neural network models that match the needs of edge computing, we are currently developing technology that allows us to exploit distributed processing and parallelism for machine learning workloads using computational storage. This work has led us to explore federated learning and transfer learning as efficient mechanisms to exploit data locality and harness the processing resources located in each one of the drives where the data resides. So I don't have time in this keynote to go into the details about this topic, but in a few words, transfer learning is a domain of AI which focuses on the ability of a machine learning algorithm to improve learning capacities on one given data set through the previous exposure to a different one. And federated learning, which was first introduced by Google in 2017 to address concerns about privacy and network congestion, is a framework to train a high-quality centralized model with training data distributed over a large number of clients. So in addition to benefiting from parallel processing, the obvious positive side effect of such an approach is to reduce data movement by limiting it to transfers or very sparse models that are updating the main model. So let's take a look at how it works. The next few slides provide a simple side-by-side comparison of machine learning training with a traditional approach on one side, the left side, and computational storage with federated learning using weightless neural networks on the other side. So training starts with loading new data that one needs to analyze. This data comes from the network or from sensors that are feeding the computing system that we have depicted here. So note that we are assuming that there is a pre-training model that is available in each case. Now, because we have storage devices capable of running machine learning algorithms, we also upload the training models in parallel to each device. So once these models are uploaded locally to each device, we're ready to transition to the next phase. That next phase is the training. So when enough data is available, training can start. On the left side, as you can see, it involves data transfer, probably a lot of data transfers, depending on the size of the model that you want to train. On the right, the training happens in situ, meaning in storage, by taking advantage of the computational resources that are available in each drive and the locality of data. Please note that this distributed system enables parallel training and no data movement occurs. In this example, there is no host CPU activity in the computational storage scenario. If we choose to use the host CPU, we could potentially augment the performance of the system at the cost of some additional data movement. That is a trade-off that has to be made on a case-by-case. Once training is complete, it is time to evaluate and update the model so it can be used on new data for inference, for example. On the right side, each one of the computational storage drives has generated a partial sparse model These models are uploaded to the host CPU so that they can get combined and create a new, updated, and better model based on the evaluation. On the left side, the process is centralized and involved all steps at once. Finally, the models are updated and ready to be used. In the case of federated learning scenario, the model can be distributed to all computational storage devices to enable parallel distributed inference. So we actually implemented a federated learning experiment in our labs. This is an ongoing R&D work at NGD Systems. I'm showing here some early results on the well-known MNIST dataset. We're currently working on other much more complex datasets. It's exciting to see that training and inference with computational storage devices can take advantage of data locality and parallelism. In-storage federated learning provides precision and generalization. We can see that the accuracy is the same as training a single model using all the data locally. And I also want to highlight the fact that after a single commit of 1,000 samples, the accuracy reached more than 90%. After only 4 commits, which represents 4,000 samples, we reach more than 94% accuracy, and that accuracy quickly converges to levels required for real-world use cases. So I will finish my part of the presentation by showing a couple of examples of machine learning applications actually running on NGD's computational storage drives. We do have a meeting room where we can show these demonstrations. If you are interested, please contact Scott Shadley. This is going to get you access to that. The first one is an object tracker implemented using a weightless neural network that is processing images from a video stream as they are stored in the drive. This is showcasing an online training as different aspects of the object are processed in real time. So we are not limited to running weightless neural networks in our drives. We have successfully ported the well-known MobileNet V2 that powers the next generation of Google's mobile vision applications. MobileNet V2 pushes the state-of-the-art for mobile visual recognition, including classification, object detection, and semantic segmentation. It is part of the TensorFlow Slim Image Classification Library that many of you are probably familiar with. The application runs in the computational storage drives, processing the images coming from live video streams. And with this, I will conclude my presentation. Thank you very much for your attention. Now back to Scott for some concluding remarks.
Thank you, sir. So as we've shown here today, and as I look at the wonderful clock we have, we apparently did things in so much parallel fashion that we're actually ahead of schedule, so you'll be appreciating that we'll give you a few minutes back of your day. But we want to talk to you about, again, just kind of reiterate, the data is not an issue of generating the data. It's not an issue of saving the data. We've got all these different companies here that are producing storage products to gather it. But you can tell by this, again, referencing a Gartner presentation, that the concept of a cloud and a cloud only and an endpoint are not the same anymore. We have a distributed network of applications, locations, types of information that are required. We have, in this case, they call it the edge computing. There's an edge cloud in there. We have the cloud. And with the capabilities that computational storage provide, you can actually migrate the ability to drive real results and real value from that data in each of and every one of those locations in some form or another. So it's no longer this black and white, I have to have it in a data center, or I'm pushing all of my work to the cloud, or I'm going to keep it all local in a private data center. The data center, as we know it, is evolving into a more distributed platform. And one of the biggest things that we can do from a storage architecture perspective is something like computational storage. And so when you think about it, you need to have scalability. It's key. So being able to have a product that delivers that and helps with this new cloud, meeting this distributed edge. Edge data growth is going to continue to have emphasis on hardware platforms. There's been examples, especially as Vladimir pointed out with the carbon footprint problem, where we can deploy lots of hardware to solve our problems, but those hardware adds come at a cost. There's a CapEx cost, there's an OpEx cost. there's even a footprint cost associated with all of those. So being able to come up with innovative ways to overcome that, either in new and innovative form factors like the EDSFF, and Jonathan was kind enough to give us a little bit of background on that since he helped found that footprint, but also the density that is available for those. So then you get into the conversation as well, how much is too much to put in one device? And if you put it all in there, how do I get it all back out? You don't have to get it all back out. Compute on it where it is. Solve your problems in real time. And that's where this concept of in situ processing from NGD and computational storage as a market is really going to evolve and help drive the future of the storage technologies and architectures of today. So with that, I just want to highlight that this is a technology that is getting traction in the market. We've been recognized by our friends at Gartner, and this month we were also recognized by our friends at IDC. So the market is telling our analyst friends that this is something they're interested in. We've got a booth on the show floor later today, so feel free to stop by and talk to us about all the stuff we showed you here today and show off some more of our little toys. And of course, there's an entire day today, or this week on Thursday, dedicated to computational storage. So last year at this event, we had 4 presentations and it took up the first half of a Thursday. This year we have 19 presentations that have been, or will be given related to computational storage architecture. So as a SNIA guy, that's where I'm going to throw in the hat and say that computational storage is real, and be sure and pay attention and see what we can do to help you with your architectures and your designs. So with that, I'm going to hand it back over to Jay, and we'll go ahead on with the next presentation. Thank you very much.